Welcome back as we continue in our geared reduction overview by discussing the process of reduction. In this simple demonstration, we have arranged two spur gears to illustrate the fact that by applying a turning force to one of the gears, we will cause movement or rotation in a second gear. Simple enough to follow. We'll now change the driven gear for one that has a greater number of teeth. To be specific, the large gear has 80 teeth and the driving gear has 50 teeth. We'll place marks here for visual reference. Now we'll rotate the driver by 1 revolution, and as you can see, the driven gear has yet to complete a revolution. The driver has to move approximately another 2/3 of a revolution to have the driven gear complete its full revolution. Let's assume that our drive gear is to be powered by an electric motor that has a rated shaft speed of 1,420 revolutions per minute. What will the driven gear's speed be in RPM? To calculate this, we first divide the number of teeth on the driven gear, 80, by the number of teeth on the driving gear, 50. This calculates to a figure of 1,6, and this we call the reduction factor. Now we divide the motor shaft speed, 1,420, by the reduction factor, which is 1,6, to obtain the driven gear speed. This calculates to 887,5, the speed in RPM of the driven gear. As an exercise, let's assume that we have a single-phase motor rated at 2,870 RPM. The input shaft speed of the machine it will drive must be no more than 1,500 RPM and no less than 1,400 RPM. What reduction factor will be necessary? Well, we simply divide the motor speed, 2,870, by the maximum desired input speed, 1,500, to arrive at 1,913, the ideal reduction factor. In reality, it is more likely that a reduction factor of 2 would be used, resulting in an input shaft speed of 1,435 RPM. In practice, reduction factors are normally expressed in ratios, and in our example, we would simply say that the reduction unit required for our drive must have a ratio of 2:1. So far, we have seen that by altering the ratio between the number of teeth of a driver gear and that of a driven gear, we can achieve a speed reduction. The process has involved only 2 mating gears. We call this a single-stage reduction, or simply a single reduction. Far higher reductions can be achieved by using sets of gears in a number of stages. After the break, we'll look at various reduction methods and reducer types.